Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Nahuel Andrés with us today. Hi, Nahuel.
Hi, Frank. How are you?
I am doing well on this December 17th of 2021 as we wrap up 2021. So I'm doing quite well in Phoenix. And where are you located at, Andrés?
Well, now I am in Buenos Aires, Argentina. I am in the capital city.
Very
Here
nice.
we are in summer. Very nice day today. So I am drinking my mate. I don't know.
So explain to people, what is that? What is that drink?
Mate. So
Yeah.
the mate is like, it's a drink. You put some yerba, which is green stuffs. And then you put water not too hot, not too cold. And that's it. And you drink it. It has like mateina, which is basically like caffeine, like the coffee things, but for mate. Here in Argentina, Uruguay, and some other country, we drinking like, it's like a cost, like we do it.
Like coffee.
Yes, exactly. It's like a coffee.
I got the espresso going.
I love coffee. The only problem with coffee is I am drinking a lot of coffee. So I have to chill out with the coffee. So that's why I'm using mate.
That's very cool. That's very cool. Yeah, solstice is coming up. And so it's going to be your summer solstice. It's going to be our winter solstice, and solstice is coming. And that's pretty great. So you said you're now in Buenos Aires. Where were you before?
Well, during more or less 3 years, 3.5 years, I was in Paris. I did my PhD.
Nice.
Laboratory at plasma physics lab in Palaiseau.
Nice.
With some colleague. I'm going to present them later, probably. And I was there for 3 years. I love that part of my life. The only a little negative thing for me was the weather, because in Paris, half of the year is raining, and you have a lot of not like this. So for me, it was very not depressing, but it was a little
it's gray. It's gray.
I would like a little more of sun.
A little more sunshine. Yeah.
It was a lovely experience for me. It was very formative in different levels: social level, academic level, personal level. It was incredible.
Very cool. You have an awesome set of tattoos on your arms there.
Yes, I have a lot of tattoos. I cannot show you all.
Okay.
This is YouTube, because I have a tiger here. I have here like a lotus flower.
Oh, yeah. Very nice.
I have like a koi. The story of the koi and the dragon. This is a Japanese, Chinese story, I think, about the koi that is swimming against the river, and then when he reached the top, he exploded like a dragon. It's a very nice myth. You can Google it. This is the tattoo for that.
That is awesome. That is cool. Awesome. Nahuel, what do you like to do for research?
Well, what I am doing right now is I am doing basically plasma physics. I am very interested in the solar wind turbulence problem. This is a huge problem that you have to combine theoretical models with numerical simulation and with observation. And so I am trying to do that to complement these 3 legs. What for me is the most important part of science, try to combine these 3 levels of understanding of the universe. And for me specifically, I am very interested in the solar wind, in plasma turbulence, in plasma physics in general, very interesting. I am also interested in fluid, neutral fluids.
Sure.
But mainly now I am doing plasma turbulence with some colleagues, with some students. We are trying to,
very cool.
put it out.
And that is going to bring us to this very lovely APJ article.
Yes.
The evolution of compressible solar wind turbulence in the inner heliosphere, PSP, THEMIS, and MAVEN observations. And Nahuel, take us away.
Yes. Well, thank you, Frank. Well, first of all, I want to thank you for giving me this opportunity to tell these recent results. So, and I would like to thank my co-authors. This is Fuad Sarawi, Lina Hadid, and Sebastian Galtier. They are 3 colleagues of mine that I met in Palisson, LPP is the lab that they are there, and it has like 2 legs, one in Paris and one in Palisson. So for me, it's more or less the same. They are in Paris. Then we have a Xiong Wang, which is a colleague. Also, he's a permanent position in the Wuhan University. And then we have Norberto Romanelli, Gina Di Braccio, and Jasper Halekas. They are colleagues from NASA and I think the University of Iowa. Yes.
Yes.
So, yes.
Cool.
Oh, yes. So I would like to thank them for helping me to do this work. And if you want, I can directly start with some introduction. What we did here is basically we study the compressible energy cascade rate, which is in the solar wind, using basically 3 different data sets. One from PSP, which is Parker Solar Probe, the recent NASA mission. Then, and we combine this measurement with THEMIS measurement at 1 AU and MAVEN measurement from more or less 1.5, 1.6 AU. AU is an astronomical unit, is the distance between the sun and the earth,
Yes.
So what we did here is we use a generalization of the Karman-Howard equation, which is basically is equation that give you a way to compute the energy cascade rate in turbulence. The problem of turbulence, you can think about that like you have different scale. It's a multi-scale phenomena that relate different scales, and the most known result from this is when you have like a cascade of energy. You put energy in the large scale, and this energy goes through what we call the inertial range, and then goes to the dissipation rate where the energy is dissipated.
Yes.
So yes, sorry.
Yes.
Okay, sorry. So related to this, there is a very important problem in the solar wind community, which is the heating problem of the solar wind, the heating of the solar wind,
yes.
Which basically say that when you measure the solar wind, as you go from the sun and you go far away, you observe the temperature, and you can observe that according to the model, the temperature should follow some law. But when you measure the temperature is much higher than the model prediction. So yes. you can interpret this observational result as a heating of the solar wind. There is something putting energy in the solar wind, and we don't know. We are not pretty sure how this process goes. And yes. One of the candidates for that, of course, is the turbulent process. So what we do is basically in the MHD scale, we use an exact law that, using correlation function, compute this amount of energy that goes from the large scale to the small, where is heat. It's basically we are computing the heating rate, if you want. Yes. So for that, what we did is basically we use an exact law that I derived like 3 or 4 years ago with Fuad Sarawi there at the LPP, which the original part is the fact that we are putting the compressibility. The compressibility is basically the fact that the density has fluctuations. Typically in turbulence, we have a few results, and these are a few exact results, and these exact results typically are assuming incompressibility. Here in this work, what we did, or in the work, in the theoretical part of the work 4 years ago, what we did is basically we use a compressible model. So for that, what we used was the compressible MHD equation. You know, the MHD is magnetohydrodynamic. It's the model that we use when we are in the largest scales of the plasma, because as we go to smaller and smaller scales, more physical effect appears, and that is much more complex, you know. So we are going to stay in the MHD scale. And for that, what you can see here, or you can show, we have the 4 equations for compressible MHD model. It's equation 1, 2, 3, 4. I don't know if you want that I enter into detail, but this is basically an equation for the density, an equation for the velocity, and an equation for the magnetic field, the evolution of this field, and scalar. And also you have the divergence of the magnetic field equal to 0. Since I use a change of variable here, Equation 4 is that. It's basically nambla dot b equal to 0. It's that equation, but it's writing like a very fashion, in a fashion way, using the compressible alpha velocity. And basically you have that equation. It's not much important, this maybe for the general public, but for the one that is in the business knows what I am saying.
So question, does reconnection play a role in these calculations?
Yes, of course. If you want to study the reconnection problem, you can use this type of equation. Of course, in this work, I didn't attack that problem. If you want for reconnection, you need the equation 3, which is the equation 3 is basically the equation, the induction equation. But when you change from if you, instead of thinking of in the magnetic field, you think in the compressible alpha velocity. The compressible alpha velocity is basically the magnetic, is there exactly. It's the magnetic field divided by the square root of the density. So in that, if you do that, the positive thing is that the magnetic field and the velocity field have the same units, you know, and it's a little more easy for the math, for the derivation.
Okay.
So basically, if you use that equation, you can derive an exact law, which is basically an expression for the energy cascade rate, which is the main thing that we need to compute using in situ measurement.
I'm with you.
So if you go to equation below, I think, because you have to do, yes, well, after you assume isotropy, homogeneity, forcing in the large scales, dissipation in the small scale, a series of assumptions that usually you use. You can go to see the paper if you are interested. After that, you can obtain equation 5, equation 5 that is basically, you can see, the 5, yes, thank you. So equation 5, you can see there is an expression for the energy cascade rate as a function of different type of terms. Since we are going to deal with single spacecraft measurement, I'm going to compute only the first term, because it's the only that I can compute, basically, because the other one involve gradients and divergence of the field that I cannot do it. I need multi-spacecraft measurement for that. In fact, with the people from the LPP, we did it some years ago using MMS, but that's another work for another day. So for here, I'm going to concentrate only computing the FC terms. And these terms are, yes, exactly that one. And this FC is in equation 6, which is the equation that I am going to compute. As you can see, this FC has 2 terms, basically, because the first terms, the first and second terms are the one typical term that in incompressible turbulence you have. If you take the incompressible limit in this 6 equation, you recover the exact law from the incompressible MHD model. And the second term is the new thing, is the new result, because you can see that you have purely compressible term, because you can see that it's proportional to the internal energy, which is related to the density, and to the increments in density. And then you have the increments in velocity.
Cool.
So I'm going to compute that using the different data sets. So if you want, you can go directly, I think, to the figure 1, and I can talk about the data set, because then you have what I say is basically what I said. I'm going to compute this term only, and there is a lot of math and some arguments of why I'm not going to compute the other terms. But relate to the work, we don't need that, so we can go directly to the data set if you want. To figure 1, I think.
I have one more question. What do you?
Yes, please.
What do you use for the equation of state to relate the energy?
Oh, that's a good question. For that, what we did, that's a good question. What we did is we assume that we have an isothermal plasma.
Okay.
So from that, you have an expression for the internal energy.
Yes.
Which is proportional to the log of the density. But that's a very good question, because at the end of my talk, at the end of this nice talk, I'm going to discuss 2 limitations of this work. Yes. And one of these limitations is going to be the fact that I am assuming an isothermal plasma. but we are working in improve of this result. But I'm going to tell you about that.
Okay,
later.
cool.
Okay.
Let's take a look at the, those are the short description of the data that's used, right? Over the.
Yes, exactly. So I don't want to enter into detail, but basically we use 3 data sets, one from Parker Solar Probe, one at near the perihelion of the mission,
Yep.
which is in distance is from the sun. The distance is more or less 0.2 astronomical units. Then I'm going to use, I combine this with a THEMIS data set, which is at 1 AU. THEMIS was a mission that was around the Earth. And then I'm going to combine these 2 missions with a third one, which is MAVEN, which is orbiting
Mars.
around Mars.
Yep.
The distance is more or less 1.6. Obviously, this distance changed, but not
Yep.
so much. The only one that changed a lot is Parker Solar Probe. But I am concentrate only in measurements around more or less 0.2 astronomical units.
All right.
Okay.
Yeah.
So I use some criteria, this is not new for you or for anyone that is seeing this video. When you use a measurement, you have to use some criteria to be sure that you are not messing and you are not, putting some particular events. For instance, you can have like a shock, you can have different structures that the spacecraft here and the solar wind pass away, and you have some disturbances and shocks and things that they are very interesting, but I don't want to study them, so I make like a criteria to discard this event and only have purely turbulence events. I did this for the 3 data set, and then I combine like in a large data set. And then here in the figure 1, you can see the distribution of the density, the solar wind velocity, and the annual fan velocity for the 3 different data sets, for the 3 different missions. And I'm not going to enter into detail, but basically we are recovering the typical values that you see for this typical heliocentric distance.
Are the solid lines a fit to the data?
Excuse me?
The solid lines,
Yes, now the solar lines are, the kernel density estimation of the distribution of the histograms. You can see, I think you can see here, maybe it's a little, it's not seen clearly, but you have the histograms behind the line. The lines is the fit of this histogram, only to see, So typically we have like a slow solar wind. The solar wind has 2 types of solar wind mainly. One which is the fast solar wind, and the other one is the slow solar wind. This type of solar winds.
Yes.
This difference is related to the source of where the solar wind came. In fact, Parker Solar Probe is studying right now this type of origins. But for us, we are going to concentrate basically in the slow solar wind, because you can see from the slow solar wind is typically the solar wind speed less than 500 kilometers per second. So you can see that we have this type typically. And according to density and alpha velocity, I don't have much to say. It's the typical values that you observe. So we take, as I told you, we take this data set and we compute the energy cascade rate and the different components. If you want, you can go directly to figure 3, if I don't remember wrong.
Figure 3 is good.
Figure 3 is basically the energy cascade rate as a function of the time scale. Yes, exactly.
Okay.
So you can see here, this is the absolute value. We did that because this energy cascade rate it is related to the direct cascade of energy or to the inverse cascade of energy. You can extract information from the sign of epsilon c, but since that's beyond the scope of this work, so for this work specifically, what we did is we studied the modulus, the absolute value, the magnitude of the energy cascade rate. And here you can see for PSP, THEMIS, and MAVEN, the energy cascade rate as a function of tau. Tau is the time scale. So you can see here that you have different time scale. In particular, when you are in the largest time scale, for instance, 100, 200 seconds, we say that we are in the MHD scale. So to see a statistical study of it, you can see here, you see like 500 curves, 500 lines. This is nice to show, but you cannot do much with 500 lines. So what we did is basically we take the mean of each particular event in the MHD scale. And for us, the MHD scale is the gray shade part is between, I think, 100 and 1,500 seconds, more or less.
Yeah.
Like that. So we did that, and we are going to assume that this mean is an estimation of the energy cascade rate in the MHD scale.
Okay, very good.
So we did that. We did that. Sorry, and let's go for in figure 3. I think I compute this mean in figure 4. Sorry. Yes, thank you. So what we did here is basically I am showing you the energy cascade rate, the compressible energy cascade rate, the mean in the MHD scale as a function of the incompressible one. So
Okay,
we did that.
Yep.
To see basically if you see an increase, a decrease, or some the same behavior. What you can see, the dashed line is the linear scale. So you can see that typically from the compressible model, you obtain more or less the same amount of the same energy cascade rate that you obtain from the incompressible model. And we were expecting this type of result because, as you probably know, the solar wind typically is in an incompressible state. So the compressibility, of course, play a role, but in these cases that we study, looks like it's not much important for us, at least. But of course, I'm going to show you some impact in the compressibility. But you can see here the color bar is basically the level of compressibility, how much the density fluctuation are important in the plasma. And you can see that the most compressible, yes, exactly, the most compressible event are the one from particle solar probe, because we see that the density fluctuation increase as we approach to the soul. However, the energy cascade rate is not, at least in the MHD scales, are not very affecting by this.
Okay.
So this is the first result. In the inset, I put the level of fluctuations for the magnetic and for the velocity fields. It's only to put there because the energy cascade rate depends strongly in this fluctuation level. So I put it there. But the main result from this, which is the first important result for me, at least from this paper, is the fact that from the compressible model, you obtain basically not much increase in the energy cascade rate. It's basically the same that if you compute the incompressible one. But of course, you can go to figure 5.
Figure 5.
You can study more figure 6. Sorry, figure 6. Because figure 5 is the same, but in other words, I would like to discuss figure 6. From figure 6, you can see that in the y-axis, you see the compressible energy cascade rate. Only the part that the F2, the compressible term that I discussed before, only the F2 as a function of the F1. The F2 is the term that is purely compressible. When you kill compressibility, this term should be 0. And in the x-axis is the typical generalization of the incompressible law. So you can see here that as you increase the compressibility, when you are very purple, yes, it's purple. When you are very purple, the compressibility is very low. So the main term in the energy cascade rate is the Yaglon one, is the incompressible one.
Yes.
Effect of the compressibility. As you increase the compressibility in your plasma, you can see that the term, the dominant part, start to be like a competition between these two terms, between E2 and E1. And that's we were expecting this type of result. And you can see that this trend is the same for the three measurements.
Yeah.
So no matter the heliocentric distance that you are, you can see this behavior. So what I am expecting, if I have, I don't know, because you have to remember that the solar, we are not in a supersonic plasma. If we were in a supersonic plasma, we would have a lot of compressibility, 90%, 100%. And so I was expecting to fill this part, which is white, to fill this part of the plot. I need that, or I need simulation for that. There are people that I knew that is working on that.
Yep.
And well, this is like a basic interpretation of this plot. Then you can discuss a little more, but I don't want to get too extension. So I prefer to go directly to the last part of the paper, which is the second result for me. The second important result is basically, you can see here is the temperature for each event. You can see the temperature as a function of the compressible energy.
Okay.
And in color bar, you can see the velocity of the event, or the velocity of the plasma for this particular event. You can see basically two important results. The first one is that we see a clear trend between the temperature and the compressible energy cascade rate. As you increase the compressible energy cascade rate, you obtain much more hottest events because the temperature is much higher. So you can observe that the compressible energy cascade rate that in some way is putting more energy in the plasma as we expect.
Yep.
From that, the second one is there is a very clear correlation between the most hottest events and the velocity speed. You can see the most yellow ones are the one that is most hot. Sorry, hot.
Yes.
So these are the typical, and this in some way, this validate or this support the idea that the turbulence is putting energy in the plasma. Of course, there is limitation to the interpretation of these results. I had to say that we had at least two limitations that I want to say, because I want to be honest. The first one is the fact that for computing this, we are assuming all the time isotropy. And you know, isotropy in the solar wind is a very bad assumption, because we know that we have a mean field, and we know that turbulence is very effective because of this anisotropy. So the real energy cascade rate should be like a perpendicular cascade rate and a parallel cascade rate to this mean field. In this paper, we are not doing that.
Okay.
And the second limitation is the one that is related to your very good question, which was the fact that we are assuming a compressible plasma, and we are assuming an isothermal closure. Yep. And we know that typically the solar wind is not in an isothermal state. So the thing that recently Fuad Sarawi and his PhD student, what they did is basically they derived the exact law assuming a polytropic plasma, which is better, closure for this type of plasma. And what we are doing right now, and this is ongoing work, we are trying to use this exact law to compute the energy cascade rate, but now using a polytropic closure. Okay. And also what we are doing, and I'm going to finish with this, we are computing the energy cascade rate in the perpendicular and parallel direction to get a more anisotropic model.
Cool.
Okay, and I think that's it. I try to be clear, but please ask me or let me know if I can clarify something.
No, I think you were very clear. We covered the highlights here. So very nice. So Nahuel, I want to thank you very much again for walking us through your very lovely APJ paper. Thank you.
Thank you.
And you touched upon it a little bit there at the end. It's always good to caveat one's work. And so you mentioned a couple of the limitations of the model and a couple of directions that you're headed. But I want to, ask maybe go a little bit broader. Let's say over the next 5 years, and are there new observations coming down the line that can help with this? Are there new Parker measurements? Are there new MAVEN measurements coming on that can be done? Are there other missions that could be able to, in some sense, get a handle on the solar wind, in addition to some of the new calculations that you talked about? So where do we go over the next 5 years?
No, I think 5 years is a lot of time. I cannot prognosticate. I don't have that prediction power, but I can say in the next 1 or 2 years, okay, there are, at least from an observational point of view, for sure, about Parker Solar Probe and Solar Orbiter. These are two missions that they are, this complement work between them, because one is mainly in the ecliptic plane. And the other one, Solar Orbiter, is going more to the poles. So a clear and direct improved to this work is the fact to use new measurements from these or from these missions. These missions are getting more closer to the sun once and one, you know, as they approach to the sun. So using this very small heliocentric distance is very, very interesting to compute. From the theoretical point of view, I think that we are doing this type of thing. In fact, this polytropic law it has like, I don't know, 1 or 2 months. It's recent. It's very recent. Okay. The improved for that is, of course, including small scales. When I say small scale, it's go from the MHD scale to maybe include the Hall effect or the, I don't know, instability in the plasma, include effect like instabilities in the plasma that occurs in the sub-ion scale. I didn't talk about that, but all this work can be extended, including sub-ion scale. And for that, you have to be very clever because the model get very, very complex. So I think from the theoretical point of view that, and of course, from the numerical point of view, I have to say that they are there to validate this type of studies before going directly like blind to use it in data.
Right.
Usually it's good to first to do some simulation to see where your model goes and then to complement with the observation. But I have to say that yes, for the solar wind at the small heliocentric distance, I have to say that Parker Solar Probe and Solar Orbiter are going to be the real issue, the real business, at least for me, for this next year or 2 years. I don't want to say anything beyond that because maybe a new variant, maybe a new disease. I don't know. I don't want to be. I don't want to be very optimist because when you are very optimist, at the end you go to this. So we have to be more or less.
No. I tend to be a big optimist. So
okay, yes.
That's just me. It's all good. It's all good. Awesome. Nahuel, thank you so much. And that will do. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.